All right, welcome to the 36th and final lecture of the semester. Congratulations, you made it this far. We're going to end by talking about some reactions of alcohols. And the first one that I would like to discuss is their oxidation to form carbonyl compounds. So So generally speaking, an oxidation is defined as removal of hydrogen from a molecule. And the reagents, there are many different ways to oxidize alcohols. The reagents that are historically very significant in the sense that these were the first very practical general reagents to do this transformation, and are still significant in the sense that they still find widespread application, are chromium-based reagents. And there are two that are commonly used. So the first is chromic acid. Okay, so H2CrO4, as the name implies, this is an acidic species. So that has important implications for the product that I'll show you in a bit. The second thing is that chromic acid, very polar, always used in aqueous solution. So there's always going to be a lot of water around when we use this reagent. You actually use it, you get it as a solution in water. So this is also important for what we'll talk about. Okay, so and then the partner to that is what we call pyridinium chlorochromate, or PCC. And so I'll draw it out here. Okay, so this ring on the left is six-membered ring with the nitrogen is called a pyridine. And because it's protonated, it's a pyridinium. Okay, it's an inexpensive common base in organic chemistry. And basically you can see that this is a salt. And so you get the pyridinium cation and then the chromate anion, okay? And PCC is a nice complement to chromic acid because we can use this in an organic solvent. So, that may seem a little counterintuitive because it is a salt, but the pyridine is quite hydrophobic, and you can easily dissolve this reagent in non-polar organic solvents. So And the one that I'll use that's commonly used is dichloromethane, so CH2Cl2. Okay, and then finally, it's not acidic. Okay, at least not in the way that chromic acid is, right? And so we can draw an overall reaction, and we're going to discuss the reactions by substrate class, so primary, secondary, and tertiary alcohols, because their chemistry is slightly different. And so we'll start with secondary alcohols. And you'll recall that the secondary means that the carbon bearing the hydroxyl group also bears two carbogenic substituents, okay? So this is a generic secondary alcohol. You treat that with chromic acid in water or PCC, so I'll just abbreviate it PCC in dichloromethane, and you get the product of oxidation, so removal of hydrogen, okay? And this species has a special name. This is known as a ketone. Okay, and so a ketone is just defined as a C double bond O carbonyl with two carbon substituents on the carbonyl carbon. Okay, so PCC, chromic acid, always give you the same product with a secondary alcohol, and the mechanism is as follows. So okay, so we'll show it for chromic acid first. In the first step, the alcohol is going to attack the chromium, and I write down the oxidation state there just so we can keep track of electrons. So we're starting with a chromium-6 reagent. And what we'd say is that an oxygen lone pair attacks the chromium center, okay? And I don't want to put any more electrons. I don't want to go up to 10 electrons around chromium. So we need to break a bond. And the weakest bonds are going to be the pi bonds to oxygen. And so we can push electrons up, all right? And what that gives us is an intermediate that looks like this. Okay, and what we then say is that there's a proton transfer step. Okay, so we want to remove that proton from the attacking alcohol, but it would also be nice to neutralize the negative charge at the oxygen on chromium. And so this is, you can draw this many different ways. You could have another molecule of this thing come in and do a bimolecular proton transfer. For us, I'm just going to keep it simple, and we're going to imagine that proton is transferred directly to that oxygen. Okay, and so what you then form is this intermediate here. Okay, and this has a specific name. This is known as a chromate ester. Okay, and if we think about oxidation states, nothing has changed yet. We still have chromium-6, and I haven't oxidized my molecule at all. The next step is when that oxidation occurs. And so what we say is that the chromium oxygen with the double bond attacks that hydrogen adjacent to the alcohol. You push electrons down, and then you push the electrons in the chromium oxygen bond towards chromium. And so what you end up with is our ketone product plus CrOH, OH, OH, OH. Okay, and oops. If you work out the oxidation state, you should be at chromium-4. So you go from chromium-6 to chromium-4. You oxidize the substrate by 2 units. And so remember that, oxidation states are always conserved in reactions. You have to, if something's getting oxidized, something else is getting reduced, and vice versa. Okay. All right. So the important points about this mechanism are the first step, the addition to the chromium. Okay. And in the second step, the proton transfer, we're totally okay with you just writing proton transfer. You don't even need to draw up the arrows. If you want to, you can. But what you're going to see as you get into second semester organic is that these proton transfers happen all the time, and we don't really want to spend a lot of time on them. Anyway, you can write proton transfer, or you can draw a detailed arrow mechanism. Either way, you should go through a neutral chromate ester, and then you show the elimination. Okay. And just a comment on the elimination, it looks new and bizarre. It's very different than anything that you've seen. But let me just draw an analogy. So if I had a structure like this, well, let me draw it like this. Okay. We said that, in eliminations, we usually want to do an anti-periplanar elimination and an E2 elimination, but we can do the syn periplanar. And so this hopefully is old hat to you. You would eliminate to make the alkene. If you imagine hypothetically replacing the carbon that bears the bromine with an oxygen and replace the bromine with the chromate, you have a structure like that, and it's the same type of elimination. The only difference is that the proton is picked up by the oxygen within the chromate ester. So it's an E2 elimination, and it is very similar to what you saw with the base mediated processes. All right. I want to go through the mechanism of the PCC oxidation of a secondary alcohol. It's very similar, but it's worth going through it. So So again, we're sticking right now with secondary alcohols. Okay, so that is a secondary alcohol plus the pyridine, pyridinium chlorochromate. Okay, the first step here is a little bit different. So with the chromic acid, we attacked the chromium, broke one of the Cr oxygen pi bonds. Here we have a good leaving group attached to chromium in the chloride, and so we're not going to break any of the pi bonds. We're just going to displace the chloride with our alcohol. Okay, and that will get me to this type of intermediate. Okay, and I've now got, did I do wrong here? Displacing that, yeah, no, that looks good. Okay, I've now got this species in solution. Same thing here, proton transfer. And again, don't need to. If you wanted to draw arrows, you could just have this O minus. Oops, that's not what I want to do. You could have the O minus attack and then move the proton over there. Okay. And so again, we're going to get to a chromate ester. Okay. And this is where it's very similar to the chromic acid. So now this will just attack, push electrons down, push electrons to chromium, and that gives you your product. I must have missed 1, 2, 3, 4, 5, 6. Yeah, sorry. The chromate ester here needs to be corrected. So this is double bond O, and so this is double bond O. Okay. So again, start with chromium-6, end up with chromium-4, and the electrons come from the alcohol substrate. Okay. So the nuance with these reagents and where strategically one is better than the other, or they're just different and they give you different outcomes, is in oxidation of primary alcohols. Depending upon the reagent, you get a different product. So if you were to do a PCC oxidation on a primary alcohol, the product that you get out is what you might expect based on what we just discussed. And so you get a single oxidation, you form a carbonyl. You have one carbon attached to the carbonyl carbon, so this has a different name. This is known as an aldehyde. Okay, so and it's formed by a same identical mechanism as to what we saw with the secondary alcohols. The difference is with chromic acid. So H2CrO4 with a primary alcohol. This gives you a distinct product known as a carboxylic acid. So I now have a carbonyl, but with an OH attached. Okay. And so, you know, the question is what's going on? The important point to remember is that with chromic acid, you're under both acidic and aqueous conditions. So all right. And so if I take a primary alcohol, treat it with chromic acid and water, I get initially to an aldehyde product. So okay. And so this this is the exact same mechanism as what we saw for the secondary alcohol oxidation, but this is where the difference comes in. It doesn't stop here. So you form an aldehyde. Aldehydes are reactive species. We have water and acid around, and so the aldehyde reacts with both of those. And so there's essentially an acid-base reaction that occurs between the aldehyde and the chromic acid. So I can transfer a proton. I protonate the aldehyde, and that makes the aldehyde electrophilic. And so now water can attack. Okay, and then in a second step, the chromic acid or the chromate anion that was behaving as an acid in the first step will remove that proton, take it back. Okay, and so the point is that the chromic acid is really a catalyst here. It's regenerated. The product that you form from your substrate has a specific name. We call this a hydrate. Okay, it is the product of formal addition of water to a carbonyl. Okay, and I've used back and forth arrows throughout here because this is an equilibrium. Aldehydes are always in equilibrium with their hydrate. And once you get a little bit of this hydrate, this can go on and react with your chromic acid in exactly the same way a simple secondary alcohol was. So you can imagine if you were to erase one of these oxygens, replace it with carbon, you'd have a secondary alcohol. So for the next step, just ignore one of the OH groups. Think about it as just an alcohol. And what you end up with is just a slightly more complicated chromate ester. Like that, okay? And then this species is going to do its decomposition just like an alcohol to give you your carboxylic acid. So I'm running out of room here. Okay, So the salient point is that when you oxidize a primary alcohol, you need to think carefully about the reaction conditions. If you want to go up in one oxidation state to the aldehyde, PCC dichloromethane. If you want to go all the way up to the carboxylic acid, chromic acid and water. Okay. And then the final thing that I'll mention is just tertiary alcohols. And these are inert. If we look at the structure of a tertiary alcohol, there is no alpha proton to eliminate. So in some sense, that's easy. You don't need to think about them at all. All right, I'll pause here and then we'll pick up and record the second half of the lecture.